In this video, I am going to talk about the different types of feature selection that one can use while building statistical model. We're going to discuss the following points. First, we'll discuss the model interpretability versus the prediction accuracy. It's often an important point to discuss while building models. Then the type of feature selections and which one to be used when, and how to decide the best model out of these set of models. Subset selection, forward selection, backward selection, one of the type of feature selection. We'll talk about shrinkage methods or regularized regression models like lasso and reach model. And then how do we select the best model? By doing cross validation. We'll talk about that in brief. And then finally, we'll discuss the difference between feature selection versus dimension reductions. Often people confuse feature selection with dimension reduction. So that's one important point that we'll discuss at the end of this session. Okay, so let's get started with so what is the basic statistical model? Well, a basic statistical model has a target variable y and there are a set of predictors of features, right? So there are different names. Some call it independent variables, some call it features, predictors. So you can name any one of these names. So how many features you should have in the model? Often an important questions in any statistical model. Okay, so the one important thing to consider is you have to consider the prediction accuracy, or the trade-off is between prediction accuracy versus model interpretability. Why so? Because when you use a large number of variables, the prediction accuracy is likely to go up. Okay, but the interpretability of the model will go down. Okay, so that's the main issue or the main trade-off that lies selecting the best number of predictors in a model. Okay, so the idea is how many features or how many number of independent variables or predictors are to be there in the model. Okay, so the trade-off is whether to have less number of features or more number of features. If you have less number of features, it's easy to interpret, less likely to overfit, low prediction accuracy. So these are two good points, but the third one is the bad point or the cons, right? The first two are the pros. If you have more number of features, you should will have difficulty in interpreting. So that's a con, that's a demerit. Then it's more likely to overfit. That's again a bad thing. But we are likely to have high prediction accuracy. Okay, so that's a good thing. So how do you know that what is the best set of variables or best set of features which does justice to both prediction accuracy as well as model interpretability? And that's the idea behind this session. So what are the ways to do or select the best number of features, and how to select the best model out of this given set of features, given set of models. Okay, so feature selection can be very important in model building. So if you look at the way we measure the performance of machine learning or statistical model, it actually depends on following points. Okay, it depends on the choice of algorithm, the algorithm that we are choosing to build a particular model or to solve a particular problem, the feature selection or the method, feature selection method that we are using, and we'll see in the next slide what are the feature selection method available to us. Feature creation, important thing. So how many new features or new predictors that you're creating from the given set of predictors, right? So that could be many, right? For instance, if you have x is one of the predictor, you just created by squaring it, that's a new creation. You can take the log of it, so that's again a new feature. So that's nothing but feature creation. And then finally it's model selection. So your prediction accuracy or the performance of your model, both in terms of interpretation, prediction, more from a prediction point of view, it depends on the choice of algorithm, feature selection, feature creation, and model selection, right? And one of the most important thing is feature selection, and that's what is the topic for this session. Feature selection is also known as variable selection. Okay, in ML we call it feature selection, but it's more or less the same. Okay, so what are the feature selection methodology available to us? This basically can be categorized into three types. The first one is filter methods. The second one is wrapper method. The third one is embedded methods. Okay, and these are groups of methods. There are several techniques within each one of these groups. Okay, so what is filter method? Okay, so filter methods have several types of selection methods, and it's also known as single factor analysis. So in econometric modeling or pure statistical modeling, people call this as single factor analysis. Well, so what we do in this method, or in such methods rather, because there are several methods out there, it's not just one method, and this, remember, this is just a group of methods. We calculate or we compute the predictive power of each individual variable. So instead of combining, we just calculate, or we just measure the predictive power of each individual variable. So we evaluate that. Okay, so how do you do that? Well, there are several ways to do it. Correlation, we find out the correlation. So we find out the correlation between target variable with respect to the predictors or the features, the x variables, right? Whether it's x1, x2, or so on, right? And we have y as target variable. So we find correlation of x1 with y, x2 with y, x3 with y, and so on. Now, intuitively, the independent variable or the feature or the predictor, okay, I'm going to use just one of these name. So the feature that will have the highest correlation with y is the best feature. Okay, because we want the target variable to be highly correlated with the features, right, or the predictors, right? So that's one way of finding it out. So you just find a correlation matrix where you will have y, and then you will have x1, x2, x3, and so on, and see which one of them is having highest correlation. Correlation, by the way, lies between 0, 1, 1. So the one that has the maximum, whether it's negative correlation or positive, or the modulus of correlation, whether it's positive or negative, doesn't matter. The one that has highest modulus of correlation is the one to be having the highest predictive power. Okay, so here x1 has highest, x2 followed by x2, and then x3, right? So that's one way of selecting the best variable. So you can take the top two variables to be having good correlation and go ahead with doing your modeling. So drop x3. There's no reason to do that, but you might consider that. So that's one of the many ways of selecting variables. Information value. So this is this comes from the more from industry point of view, not from academics point of view. So in industry, people use information value, which is some sort of a transformation of your independent variables, and which finds out the ability of the independent variables or the features to discriminate your y variable, or ability to predict y variable. Okay, so the one that has high information value is to be selected. Similarly, chi-square statistics is also used for categorical variable, or more suited for classification problem. Categorical independent variable, categorical features. Okay, not target variable. All right. So the conclusion that we have drawn from the the filter methods is that the one which has high correlation with the target variable is going to have the highest preference in the model, with low correlation between predictors. So ensure that not just high correlation with the target variable, also have low correlation with independent variables. So x1 and x2 should not have high correlation. So that's another point to be considered. But then here, in filter method, you don't actually look at two variable at once. You just look at just one of them and compare that with your y. So it's more of an univariate analysis. Higher the IVs, better is the variable. Okay. Wrapper methods uses combination of combination of x variables or features and find out which one is the best combination. So instead of finding out the best variable, it find out the best combination of variables. Okay. So predictive power of variables is evaluated jointly. Okay, so we can say that okay, jointly x1, x2 and x5 are the best features among the set of 10 features. Okay, so that's the way we analyze this. Okay, so it is joint evaluation of variables. And there are several methods available to us. One is subset selection, second one is forward selection, third one is backward selection, and we'll see each one of them, and we'll also take an example and do it in R just to give a demo of how this method works. And in embedded method, which is the third one, we'll also talk about it in brief. We'll go to the details of it, but we'll talk about it in brief. So this is an inbuilt variable selection method, so we don't have to take any decision. So in wrapper methods, we have to take a number of decisions, and I'm going to talk about all these three methods. So we'll see that several decisions have to be made while doing this analysis, whereas in embedded method the decisions are taken by the regression algorithm or the estimation algorithm. So it's very much inbuilt or automated type. Okay, so it's easier to use. So without one having to select or reject, so one may not have to select or reject a variable, right? So algorithm does that for you, and that's one of the technique of selecting the best features. It's also known as regularizations, and what I've heard about regularizations. So it controls the value of parameters. So the not so important variables are given very low weight or sometimes zero weight, and that's why they get eliminated from the model. So the elimination process is very much inbuilt or very much automated. So you are, as a modeler, need not have to take a lot of decisions. So it's also known as shrinkage method. We'll talk about it. The famous ones are lasso and ridge regressions. We'll talk about it in brief at the end of this, at the last part of the session. So the idea is to have optimal number of features. Okay, so that's the point. So an ideal model should have good prediction and yet not very complex to interpret and use or to implement. Oftentimes in industry, you have problem of implementation or interpretation, right? So if you are building a model which, let's say, it's an image recognition model, right? It's more, used in tech companies, image recognition. Their implementation may not be a challenge. Okay. Because you have good infrastructure, you have a very high infrastructure to cater to high dimensional space, that's okay. But if you are building a model in banking, rather evaluating or quantifying risk in banking or financial or insurance organizations, it's very difficult to implement overly complex models. Regulators are going to have questions. Even your business people in business who are going to use your model are going to find it very difficult to use your model, given that you have made it very complex. You have so many predictor variables, you have so many variables artificially created, so that's going to be difficult. So the idea is to have a good prediction and simple model, right? So we'll use subset selection, shrinkage and dimension reduction, and we'll talk about it in detail. So what is subset selection? So in subset selection, you fit models with each possible combinations of p features. Okay, let's say we have p number of independent variables or p number of features. The total number of models that you will be having is 2 to the power 3. If you have 2 features, if p equal to 2, then the total number of model will be 4. So the idea is to use every combination, right? Let's example, we have x1 and x2. We have only 2 features or 2 predictors. Okay, so how many models you will have? You will have a model with only x, with only with only x1, with only x2, and with both x1 and x2. So this one is the first model with only x1 as the predictor, and second model you have only x2 as the predictor, and third one you have x1 and x2 as the predictors. So that 3 model. We ideally should have 4 model. Well, the fourth model is nothing but only the intercept. Okay, so it's just a mean intercept. Okay, it's beta. It's only the mean. So your y is nothing but the mean of your so your y hat is nothing but just the mean of y. Okay, so that is considered to be the null model. Okay, if familiar with statistical analysis, you must be familiar that in the result you always get a null model. Okay, so that's the fourth model we're talking about. So every time you're going to have 4 model, we are going to have 2 to the power p models. You have where p is the number of features you have. So that's subset selection, and it's very difficult because if the p is, let's say, 3, then total of models is going to be 2 to the power 3 is equal to 8. If p is 4, then it's going to be 16. If p is 5, it's going to have 32. But if p is 10, you're going to have a very huge number of model, and that's very difficult, right? So it requires a massive computational power, and not always you have availability of massive computational power. So to reduce the computational power, the algorithm is broken into 2 stages. So what it does is, in first stage, first all combination of models that has only k predictors out of total p predictors. So, and pick the best model from the set of k predictors. So what happens is that now for each one of these model, let's say you have p, let's say p is equal to 4, right? So there are 4 predictors: x1, x2, x3 and x4. Okay, let me okay, now let's, for instance, we have models where we have just one variable. So we will assume that as k. So let's k equal to 1. That means say one variable model. So y is a function of x1, then y is a function of x2, y is a function of x3, and y is a function of x4. So when k equal to 1, you have 4 models, and you'll have to choose what is the best out of these 4 models. So the first step, you just compute the 4 models and pick the best one of them. When k equal to 2, you have y is a function of x1, x2, and then in the second model y is a function of x1, x3, and then x1, x4, and then x2, x3, and then x3, x4. So there are going to be 4, 5 models, right? And then you will select the best out of these 5 models. Alright, so that's the way you calculate the first stage. Okay, and the second stage, out of whatever whichever model has been selected from each case, like when k equal to 1, let's say this model has been selected. When k equal to 2, the second model has been selected, and when k equal to 3, you will have another model to be selected, right? When k equal to 4, then you will have only one model, right? When k equal to 4, you will have x1, x2, x3, x4, only one model, right? And that is going to be the final model. So for each k, you will have one best model out of these groups. In the second stage, select the one that is best out of this one. So when k equal to 1, you have one model that is best out of this group. When k equal to 2, you have one model that is best out of this group. And then you will, for p variable, you will have such p number of models, right? Best set of models. Select the best out of it. How do you select the second stage models? Just use one of these, metrics, whether it's RSS in the case of regression model, cross validation error, adjusted R square. So you can use any one of these metrics to find out the best one, and it will be more clear when you take an example to understand. So one important thing to remember is that use test error to calculate or to evaluate the best model, right? When you have several models, right? Here you can see the several models, like model 1 with just one predictor, model 2 with two predictors, model 3 with three predictors, and so on, right? From each number of predictors, you will have one best model, right? With one predictor, you will have one best model out of p models. Okay. So the way to select the best model out of the set of models is to use test error, not to use training error. Okay, because you are building the model in training data. So if you use training data to select the best model, that's going to be very biased. So use test error. So RSS and R square has to be it has to be evaluated on test data set, and the one that is giving the least test error is going to be selected as the final model. A few important points to remember. The RSS and R square, right, has monotonic relationship with number of variables, and that's the worst part of this exercise. That if you keep on increasing the number of predictors or features, your RSS is going to go down, your R square is going to go up. Then what's the point of doing all these exercises, right? Now that has to be corrected by using test error, not by using training error. So you will see that monotonic relationship won't be there in the test data set. Okay, and you can actually take an example and see that monotonicity will not be, or most of the times will not be valid for test error, but for training data set it is going to be monotonic. So never use that. So hence use test RSS for regression problems and test deviance for classification problems. So depending on what type of problem you're dealing with, just use one of them. Okay, what's the problem with subset selection? As we have already discussed, it's problematic when you have high dimension, or when the number of features is greater than 20. It is like very difficult to do the computation. It's almost impossible, right? So best subset selection is impossible when p is greater than 20, and that's where you're going to use what is known as stepwise selection. And there are three types of stepwise selection. One is forward stepwise approach, backward stepwise approach, and then third one is hybrid approach. So the forward stepwise approach is like this. We start with a null model, and then you keep on adding predictors or features to the model one at a time. This is important to remember, and choose the best model among the best of k based on RSS. Okay, now you remember how you took k, right? When k equal to k equal to 1, you have p number of models, right? Because with x1 you can have one model, with x2 you can have one model, to xp you can have another. So you have p number of models in such way. So one of these models will be the best, right? When k equal to 2, then you take two variables at a time, x1, x2, then x1, x3, and so on. And then we'll have one model from that, right? So we have shown that here in this table. So when a one variable model, let's say x1 is the one that gives you the best model. Okay, now what happens is, if that gives the best model, then that is retained in the model. It never gets dropped. Okay, so in forward stepwise, you retain that model, and it's highlighted in in bold. Okay, when it's a two variable model, subset selection gives you x1 and x3. Okay, in forward we just added x2 and saw whether that is actually working fine or not, because for a two variable model x1 x2 does a good job. So we just added x2, and once that retains in the model, that never gets dropped. So in the third model we have x1 x2, but x3 was not part of it, which directly went ahead with x4. And the fourth model with four number of variables, you can see x1 x2 x4 and x5. Okay, so there is no x3, so x3 got dropped here, and you do not have x3. So x3 did not meet what is known as an entry criteria. Okay, but that's not the case in subset selection. In subset selection, you can see variables having different selection. Like in one variable case you have x1, in two variable case you have x1 x3, in three variable case you have x3 x1 x3 x4, in fourth variable case you have x1 x2 x3 and x5. So what happens is that a variable can be part of it, or it can be not part of in the next model. Whereas in forward stepwise selection, if it is there in one variable selection, it will definitely be there in two variable selection, right? Now if you look at subset selection here, x4 is there part of three variable model, but it's not part of four variable model. So that will never happen. It's not part of variable. You can see there's no x4 here, but here with three variable it's there, but that will never happen in forward stepwise. In forward stepwise, you can see if it's their part of the three variable model, all three variable x1 x2 and x4 are a part of four variable model. Here you can see x1 x2 and x4, they're all part of the fourth variable model. So here three variable model is just a subset of four variable model. Two variable model is a subset of three variable model, and one variable model is just a subset of two variable model. That's the difference. Slightly confusing, but when we actually do it, it is going to be clearer. In forward stepwise, the selection is constrained, because you cannot have just random selection of variables. You cannot have just x1 with x2 and so on, and then x1 with x3. The x2 is there in the previous model, it has to be there in the next model. So then what happens is that you already have x1 x2. So the only selection that you will be making in the three variable model is that just choose whether it's x3 or whether it's going to be x4 or x5. So the number has come down, right? Because it's constrained now. The first two places is already taken, because it's coming from the second variable model, right? But in subset selection, you can have any any combination, and that could be a number of such cases. So less candidate models are there for selection, and it comes down to instead of exponential number where it was p2 to the power p, as we have seen in the subset selection. Now it has come down to 1 plus p multiplied to p plus 1 divided by 2. So this is much less compared to this one. Sorry. So this is very high dimension compared to this one, especially for given p greater than 20. This is very easy, right? So when p equal to 10, in stepwise that we just discussed, in forward stepwise, we have 211 model, whereas in subset selection, just because you have just too many combinations and there is no constraint, right? So remember the constraint we talked about, that the third variable model has to be the subset of the fourth variable model. Similarly, the second variable model is the subset of third variable model, right? That constraint is not there. Hence, in subset selection, we have over 1 million models. So estimating million models is very tough, whereas estimating 211 models is comparatively much easier, right? That's why forward stepwise regression model is preferred for variable selection, especially in given in high dimension. But if you have smaller number of dimension, let's say p equal to 5, you can always go ahead with subset selection. It's much easier. Then backward stepwise regression. Okay, so this is one type of selection method, variable selection method, which is reverse of forward. You start with all predictors and then you drop one at a time. So in forward, we start with one, then you go to 2 variable model, 3 variable model, and so on. And it's just the opposite. You start with p number of variables and then p minus 1, p minus 2, and so on. So here is a comparison. We have backward stepwise, we have forward stepwise. So you start with all the predictors available. Let's say you have 5 predictors, x1, x2, x3, x4, x5. Now here in the first step, we found out that x2 is a bad variable or not so important or the least important variable. It gets dropped here. So we have x1, x3, x4, and x5. If a variable is dropped, it never gets added again. Okay. So in the 4 variable model, you find that x2 will never be there, right? So you cannot have a 4 variable model with the presence of x2. So that's also a constraint, right? This is also a constraint. So you cannot have a 3 variable model where x4 has been dropped from the 4 variable model. So you cannot have x4, a combination of x4 in the 3 variable model. So that is, constraint out, or that is, taken out from the selection itself. And that's a constraint. So the number comes down. Similarly, for second variable model, x3 cannot be part of it because x3 gets dropped in the third variable model. So here x5 gets dropped, so it cannot be present in the 1 variable model. So in the 1 variable model, you ideally should have 5 models, right, as per the subset selection. But here you will only have x1 with x2, with x3, and with x4. You cannot have a model with x5 because it's not part of it. I'm sorry. I'm really sorry. So it cannot have x2 either. You cannot have x4 either. You cannot have x3 either. You only have x1 because these variables have been dropped previously, right? So x2 has been dropped in the first one. X4 has been dropped in the second. X3 has been. So you cannot have 4 models or 5 models. You can only have x1 because x1 is the one that is never dropped in the previous times, right? In the last 3 or 4 steps, x1 hasn't been dropped. So in the final model, you can only have one choice or one model in that case. On the other hand, forward, you just do the exact opposite, right? You start with one model and then keep that model, keep that variable, and then add another variable. Okay, so in 2 variable model, x1 has to be there. In 3 variable model, x1 and x2, which have been retained in this 2 variable model, has to be there in the 3 variable model. So you can see this is definitely there. So it's exactly the opposite of backward. So computational power requirement is similar to that of forward. Okay, and the selection method is through RSS and Debians that we have discussed. And the comparison between forward and backward is that you have more choices now. So you build a model with backward approach, you build a model with forward approach, and then you take the final model from backward and take the final model from forward, and then compare their, do the cross validation with test data and see which one is doing it, giving you the best prediction, and just take that as the final model. Okay, so you can also combine forward and backward. And it combines the features from both types. Okay, in forward you have variable which is included never drops out, right, in the next step. In backward, a variable already dropped from the model never shows up in the model again, right? If one variable has been dropped in the first step, it will never show up in the second step. Similarly, if one variable has been added in the first step, it never drops. It has to be there in the next step. So it combines, the hybrid model combines both. Okay, so hybrid starts with adding one variable at a time like forward, but drop variables during the process. Okay, and if a variable gets dropped, it never shows up again. So it combines the features of both or the qualities of both this type, forward and backward. Okay, so it's more like subset selection. So it takes more combinations, right? So it's more like subset selection, which takes both forward and backward approach, but it has the it has the computational advantage. That means it's not as computationally intensive as that of subset selections. So instead of using subset selection, you can instead use hybrid, which does more or less like subset selection but with less computational requirement. How do you choose the best model? Okay, once you have, now we have gone through several such steps of selecting variables, right? How do you choose the best one of them? Cross validation, right? And there are several of them. You can use K4, you can use leave one out cross validation, you can use bootstrapping as well, and the metrics that one should use could be R square, the AIC and BIC. You can use confusion metrics in the case of classification, accuracy, and so on, concordance and so on. So there are several of them depending on the problem that you are working, the industry that you're working with. You have several different metrics to choose from. Okay, now we'll take an example. Now that we have some idea about the theory, we'll take an example to understand it better. So we'll take a data set and we're going to use this data set, and we'll demonstrate these algorithms and see how it works. So we have this heater data. So there are several variables we have. So it's about the salary of baseball players in US, and it depends on many things. It depends on the different aspects of the players and the different different predictors which predict the salary, which is the target variable for the given basketball player, okay, or the NBA player. Now we're going to use first subset selection, okay, and we're going to use this function reg subset, which will do the subset selection for us, okay. And then we'll see the summary statistics, we'll see the R square values, and we'll plot the BIC values, the Bayesian information criteria. We can also do the Akaike information criteria or squash Bayesian criteria. So this will help us selecting the best model. Okay. Now it's very simple, syntax is very simple, right? You can see the function is reg subsets and salary is the target, and we are going to use all 19 variables. Probably we have used 8, I'm not sure whether it's okay. If I going to use all variables, you have to give a maximum, otherwise it's going to keep it down actually, okay, because if you have large data set, the computational power is going to be massive. Given that it's a small data set, we can actually use 19 variables, which is okay, but if it's a large data set, it's going to be, so that's why it restricts to only 8 variables. I'm not sure whether I've used 19 or 8, but let's see. So I was 8 actually, okay, I can extend it to 19, not a big deal, okay. So you can see when k equal to 1, so one variable model, you will have 8 different models, right, with each one of these variables in place. Okay, now you can see out of these 8, this gives the best model. So from the first, when k equal to 1, you have the best model with CRBI. So your salary is best predicted as a function of CRBI. So that's one of the predictors or features, okay. When you have two variables models, you have many number of models, right? When k equal to 2, so you can see star over here, hits, and then CRBI. So when you have two variable model, the best prediction is given by the function of CRBI and then hits, okay. When you have three variable model, you have hits and then you have CRBI and then you have putouts. Okay, when you have 4 variable models, you have hits, you have CRBI, you have division, and we have putouts. Okay, so that's the way it goes to 8 variable model. There are total 19 of them. You can actually extend that to 19. So for that you just have to use this syntax nvmax. Okay, and then out of the 19 finalized model, you have to choose what is the best one. Okay, how do you do that? Simply do the r square. Just plot the r square or the adjusted r square. Okay, and we'll do that for test data, not for training data. Okay, so when you do that, you get r squares values. So here we have taken training data, not test data. If you have test data in place, you better do it on test data. But even if you don't have a presence of test data, you have smaller data set and you can't divide into training and test data, still you can use. When you do a summary statistic, you can see the r square value is actually going up with more number of variables. So that actually is failing us. This actually is disappointing us by saying that we are using subset selection for bringing down the number of features. Because if that's the case, the prediction power is going up with adding more number of variables. So adding more number of variables is actually good. That's ideally is the thought process. However, this can be validated by plotting the BIC value, and that's where we have done. So we have plotted the BIC value. So wherever you see the BIC, this dark spot actually touching, you see this is one case, this is one, second, third, fourth, 5, 6 or 7. Okay, I think 6 or 7. So either 6 variables or 7 variables is actually giving you the best model with a good interpretation. So BIC actually penalize you for having more number of variables. Okay, so with this plot you can actually find out what is the best model. Remember, this is all required when you are using training data for validation, which is actually not the ideal thing to do. But you already have a test data, you need not do this. What you need to do is that just calculate the the root mean square error, the RMSE, for the test data set for each model. So for each model over here, okay, you have 8 models, right? For 8 models, calculate the RMSE for test data for each 8 models and choose the one that gives the least RMSE. Okay, so the idea here is minimum of or RMSE. Okay, so that's the idea. Okay, now we'll compare forward and backward. So we just started with subset selection. We'll do forward and backward. Syntax is same except the fact that when you do not use any method, by default it takes subset selection. When you use methods forward, it is going to do forward selection. When it's going to use method, syntax is wrong slightly, this method ME, backward, then it's going to give you backward regression results, and that's what we are going to see. So here you can see that if something is added, like this is the forward one, if something is added, it never gets dropped. Now you will see CRBI has been added in the first model. When k equal to 1, you have CRBI in the model. Now you can see CRBI is there in all models. Now you can see it's star in all models, right? And that's the beauty of forward selection. It constrains that in all selection, all types of model, this has to be there. But you see that's not the case in subset selection. In subset selection, you can see CRBI is there in first model, definitely in second model, third model, fourth model, fifth, sixth, but not in seventh model. You can see this is blank. Not in eighth model as well. Okay, because it can have any type of combination. So that constraint is not there. Whereas in forward selection, if a model is added in the first case, when k equal to 1, CRBI is the one that is giving the best model. That will be there in all the subsequent models. And that's what has happened. In the second model, you can see hits get added, right? And you can see in the subsequent models, in all subsequent models, you have hits as one of the independent variable, one of the features. Similarly, the third model, you can see what is there in third model. Okay, we'll see it here. So in third model, put out is there. So you can see in all subsequent models, put out will be there. Okay, so that's the main idea behind forward selection. Okay, so again, if you're using training dataset, just look at the BIC plot and see in how many cases it's giving you the best prediction, and then choose the one. Otherwise, you'll have monotonic relationship. That means your R square will simply be improving over number of with increasing number of features. So BIC plot is going to tell you what is the best set. But if you have test data in place, just easy, right? Calculate RMSE and find out what is the minimum RMSE for which set of models, which set of predictors you have minimum RMSE, right? So it might happen that it may not be just final 8 variables, it could be 6 or 7, which is less. So few variable gets dropped. That's the idea here. Some variables get dropped from the model. So you have simpler model. Okay, now that we have seen the different types of these selection methods, let's go to the last one, which is the embedded method. Okay, also known as shrinkage method. We also call this a regularization regression models, and I'm going to give you what regularization is. One video I have made on regularization. If you want to learn more about regularization, it's there in this video in the description section. So it's a technique that regularizes the estimates, or it shrinks the coefficients to 0. So you have beta coefficients, right? These beta coefficients will be very close to 0 or either equal to 0 sometimes. And that actually, whenever it's equal to 0, then that variable is as good as not present in the model, or that variable is considered to be not part of the model. That's one type of selection method, right? Or rejection method rather. So how do we do shrinkage or regularization? Well, there is a slight change to the estimation process. So in the estimation, in the linear regression estimation, or any regression estimation, when you're using least square estimation, you are basically minimizing the root, the RSS, right? The residual sum of squares. And how to compute the residual sum of square? Is the summation of sum of 1 equal to 1 to n, yi, which is target, minus beta naught minus summation of j equal to 1 to p, where p is the number of predictors, beta I xij. So this is the set of features or set of predictors. These are estimates. Beta naught and beta I are the estimates, right? And this is how you compute your RSS, root mean square error. In embedded method, you just add another term. So this is the term that we are adding to the RSS. So RSS is computed like this in normal least square estimation. In shrinkage method, to the RSS we add another term and then minimize, and then we minimize the whole thing. Okay. Now what is the idea behind this? Well, the idea is that to ensure that the beta values get low value. So beta should get low value. And what is the benefit of it? Because what happens is that some unimportant variables which are having very high impact on your target variable should get low value, so that it gives a better prediction. Okay, and there are basically two types of shrinkage method, lasso and ridge. So lasso is the one. So this is ridge method. This is called the one that we have seen, ridge. In lasso, we just do a slight change. We just add RSS, and to that we add this term. So instead of squaring the beta, summation of beta, we have taken the summation of square of beta values. So here we have taken the modulus of that, modulus of betas. Okay. Now we are minimizing this, minimizing RSS plus lambda and the summation of modulus of betas. So this is the difference. Here it's modulus and there it is square of the parameters or the coefficients. There's fundamental difference between that. Okay. And what is lambda? It's called tuning parameters, and we'll talk about it later. Okay, so in lasso, so the earlier one was range, where your betas will tend to be 0 but will not exactly be 0, whereas in lasso here some of the coefficients, some of the betas will be 0, exactly 0. So when the coefficient is 0, that variables with which this coefficient is associated is actually getting dropped from the model, and that's the selection method, right? That's how we reject some of the variables. So we reject variables which have betas equal to 0, and it's automatic. You don't have to do it. Like in the previous case, in subset selection, we had to run it, we had to check the BIC plot, we had to check the R square, do the cross validation and so on. Here we don't have to do anything of anything. So in the estimation procedure itself, we found some of the beta values to be 0 by changing the estimation function or the cost function. So this cost function now is changed, and it automatically takes care of the variable reduction. Okay, so given that beta values becomes 0, lasso is considered to be a variable selection, not rees, although rees also is sometimes considered to be very helpful, but from a variable selection point of view, lasso is actually very useful. So beta is 0 for unimportant variables. So that's the idea here. Now important thing to remember is choosing the tuning parameter. Now tuning parameter is something that helps you in the estimation process, and you can have several tuning parameters. You can have large set of tuning parameters. Okay, so what usually you do in while building the model is that you choose you have a grid. Let's say your your lambda lies between 0.001 to, let's say, 100. So for every interval of 001, you choose a lambda value. So this is a grid, and for every lambda value, this estimation process will happen, and then it will internally do the cross validation, and will find it out for us that for which lambda we are going to have the minimum of the cost function, or the minimum of the this particular value, RSS plus summation of this beta and so on, right? So it's a slightly computationally intensive process, because for these many lambda values you will have separate optimization happening. So slightly computationally intensive, but finally you will get the model which has the tuning parameter giving you the best model, and that's done through cross validation. And again, it's good to do with test data, not with the training data. So automatically you get for the test data, but you have to replicate that with training data. You have to replicate that with the test data. Finally, we'll see the difference between dimension reduction with feature selection. Now we have learned the different types of feature selection, right? How do you select the best set of features? Okay, sometimes we can get it automatically. Sometimes you can do it univariate, use univariate analysis, and sometimes with selection method like subset selection or by stepwise selections, right? So these are the 4 things that we learned. Now some people confuse that dimension reduction is also very similar to feature selection. Dimension reduction is actually different. In dimension reduction, you do not drop any variable, okay, or you do not select the variable out of the set of variables. You actually combine. Let's say you have 4 variables, x1, x2, x3 and x4. So principal component analysis is one of the dimension reduction variable. There could be other dimension reduction with methods like your factor analysis and so on. So using PCA or principal component analysis, you can actually combine these 4 features in such a way that it reduces to a smaller set of features. Okay, so here by combining x1, x2, x3, x4, we could find 2 different variables called g1 and g2. So combining 4 independent variables of 4 features, we could found two different independent variables or two different features, Z1 and Z2, which together retains the prediction power of all four variables. So the prediction power of x1, x2, x3, x4 combiningly is retained by G1 and G2, but they are two different variables. So this is a linear combination of some of these variables, and G2 is also a linear combination of some of these variables. So we are combining variables to find principal components. Okay, but we are not dropping x1 and then going ahead with x2, x3, x3. So that's not happening. That's what happens in feature selection. Whereas in dimension direction, you combine variables to come up with composite variables or two completely different variables. So these are G1 and G2 are composite variables which are some sort of a linear combination of x1, x2, x3 and x4. And then these variables retain the prediction ability of the initial variables. But the bad thing is that you can no more interpret the original variable, because that's now combined together with some sort of a linear combination. But from a predictive model point of view, it actually does a good job, because it reduces the number of features finally, but not through feature selection, but through dimension direction, because we are bringing down by combining features here. Okay, so that's the difference, basic difference here. Thank you so much, and please subscribe to us.